All right, yesterday we did section 1, derivatives with logarithms. Today we're doing integrals with logarithms. So let's look at this. So with this, I mean, the first idea, as always, the idea with an integral is to think, what function would I take the derivative of to get this function? And so with this idea right here, first off, remember, if you need to, any plane number that's multiplied on the inside can just be pulled out to the outside. So we can rewrite this, if we want, as 2 times the integral of 1 over x dx. And we know that the integral of 1 over x is the ln of x. So with the 2 just stays there. So that's pretty much the answer. What is it, though, really? Really, you need the absolute value, right? Since you can't take the logarithm of a negative, but you still want to be able to do that. So technically, we need that absolute value there. But that's one of those things that people don't worry about so much. Or at least I never worried about so much. So, just remembering that the integral of 1 over x is ln of x, not using the power rule. All right, so this one is pretty much the same idea. We're going to do a little u substitution to help ourselves out. So we're going to make u really the only thing that's even there is 4x minus 1. And always looking ahead when you choose the u, because you see that now when we do that substitution, we're just doing the integral of 1 over u. We just have to make sure it all works out. So how do we make sure it works out? Well, du is equal to 4 dx. So we could say that dx is du divided by 4. So then we replace this dx with du and a 1 over 4. Then we'll just proceed how we did last time, is we have a number. We'll just pull that out to the outside. So we're just doing the integral of 1 over a variable. And that's going to be ln. So it's 1/4 the ln of, again, absolute value of 4x minus 1 plus c. And that's it. Now, the beautiful thing about integrals is we can check ourselves easily by taking the derivative. So if we took the derivative of this function, what would happen? Well, it's the ln, so we'd have 1 over 4x minus 1. We still got the 1/4 just on the outside, so 1/4, 1 over 4x minus 1. But then we're going to have to multiply that by the derivative of the inside, which is 4x minus 1. And the derivative of that is 4. So that's why these 4's end up canceling. That's why we needed the 1/4 on the outside. And we just end up with the 1 over 4x minus 1. Beautiful. So here we're going to try to do a similar idea. Find the area under the curve bounded by that graph between the x-axis and x equals 3. So, I mean, I'm not even sure what that graph looks like, but just to show, we're going to be trying to do something like this. Find this area here between 0 and 3. But that's an integral, right? So we're going to have the integral from 0 to 3. Wait, why 0 to 3, though? Between the x-axis and the line x equals 3? So they're saying somewhere it crosses. Do we actually have to find these points that it crosses? We have to find where it's equal to 0. Okay, well, so yeah. When we have to find where that's equal to 0. So if we set this whole function equal to 0, when is this function equal to 0? When x equals 0. So to be more specific with our graph, it seems like it's probably going to look something like this. And we're trying to find this area right here. Okay, so we're doing the integral from 0 to 3 of x over x squared plus 1 dx. We just have to solve that. And we're going to do that the same kind of way we did last time. We'll do u substitution. So I guess generally, you might want to think that your u is going to be your more complicated thing. So in this case, we're definitely going to want u equals x squared plus 1. So that our du is 2x dx, just by taking the integral of both sides there. And then I like that strategy we did last time. So I'm going to solve for dx here. I'm going to divide both sides by 2x. So I know that dx is du over 2x. So then when I make my substitution, what am I going to have? Well, look at how we're going to have x over x squared plus 1. Wait, why am I rewriting that? We're going to have x over u, because that's what x squared plus 1 is. And then we're going to replace the dx with du over 2x. I mean, that's legit, because we get the x's to cancel. So honestly, that's not the way that I usually think about it. The way that I usually think about it is that we need to find this. And right now we have x and dx. So the only thing missing is that 2. So we've got to put the 2 here, which means on the outside, we've got to divide by 2. I think that shows it better. That's how at least I learned how to look at it. Because then you say, here is our entire du. So we're going to have the 1/2 on the outside. We still have the integral. And then that entire circled thing is our du. And then we end up with 1 over u, because that's what we made the u into. And we would have got that the same thing. We would have got the same thing the last way we did it, because the x's would have canceled. But I think this is more proper. And the last thing you'll notice, we haven't done the 0 and the 3 yet. So in my mind, this is kind of an optional step, because we could just do the integral as we normally would and get what the integral is, and then plug in 0 and 3, and that's all fine. But one thing we can do that does speed things up a little bit is, and actually this is true, if we put this 0 and 3 right here, that's not really correct. These things are not equivalent to each other, because up here we're doing the integral in terms of x, but down here we're doing the integral in terms of u. So if we want to do this properly, we need to rewrite those things in terms of u. And that's fine. That we just use this equation. So you plug in the x values. So you plug in 0, and you would get that u equals 1. You plug in 3, you would get that u equals 10. So that ends up being easier, that now we don't even have to plug x back in. We can just solve this in terms of u. So now we can just take the integral, which is ln, as we've been doing. So it's going to be 1/2 the ln of u from 10 to 1. So then you're just plugging in your numbers. 1/2 the ln of 10 minus the ln of 1. And the ln of 1 is 0. So we just end up with 1/2 ln of 10. Or if we wanted to go and use the rules, we could say the ln of root 10. And that's the deal. So the basic idea, in my mind at least, is you take the derivative of your u to see what du is, and then you have to find it in here. And if all you're missing is a number, you can just multiply by the number and then divide by it again to cancel it out. All that really matters is that the x part is the same. You just need to be able to build the whole thing. But you can't multiply and divide by a variable. You can only do that with a number. Should we check our answer? So what were we solving? We were solving... I'm going to go to Desmos. We were trying to solve the integral from 0 to 3 of x over x squared plus 1 dx. Look at that. Was that the ln of root 10? Well, I want to look at the graph first off. X over x squared plus 1. Yeah, so you see our idea. Oh, it actually goes back down. That's interesting. But that was our idea. We're just finding that area from 0 to 3. And we said, hopefully this is the same as the number above. The ln of the square root of 10. Boom. Beautiful stuff. Beautiful stuff. Whoa. Now we just got a bunch of practice in a row. Bunch of practice in a row. So it's all about choosing the right U. This actually looks like it's going to be very straightforward. So here, like I said on the last one, generally you're going to make your U your just more complicated thing. So if we say that U is that, then du is 3x squared plus 1. And choosing that really is a bit of trial and error and a bit of looking ahead. Like you have to be able to look ahead really quickly and say, well, if we made this our u, so this is just 1 over u, we have perfectly our du right there. So this is just the integral of 1 over u du. So it's just the ln of u plus c. So it's the ln of what we said u was. X cubed plus x. Okay. Now b's looking interesting because I bet we could simplify that. But also look at how simple, look at how straightforward it is. Can we simplify that? What is secant divided by tangent? Is that one of the known ones? Let me think about my diagram. We got sine, cosine, tangent. This is secant right here. Yeah, so cosecant is secant over tan. So this is cosecant times secant is 1 over sine times cosine. Okay, so that really can't be simplified very well. But otherwise, we wouldn't even want to, because look at how beautiful this is. If we just simply make u tangent of x, then our du is secant squared, and that's exactly what we have on top. That's like what probably all of these problems are. So that means we're just taking the integral of 1 over u, just like we were before. So it's just the ln of the absolute value of tangent of x plus c. So look at c. C is kind of going to be similar, but again, like look ahead. So if we made the bottom u, then du would be 2x plus 2. And look at how we have that on the top. It's just like if we don't have the 2. So we're going to go, I'll change colors here so it's a little clearer where we are. U is x squared plus 2x. So du is 2x plus 2 dx, or 2 times x plus 1 dx. So look at how all we need to do is multiply by a 2. So we put a 1/2 on the bottom to cancel it. But that means that all we're doing now is 1/2 the integral of 1 over u, just like the rest of them. So it's 1/2 the ln of u, which is x squared plus 2x plus c. Yeah, easy enough. And then d is like almost like going backwards. This is like the second problem we did about this. So we just go u equals 3x plus 2. du is 3 dx. So we're missing the 3. So we pop in the 3, divide by the 3 on the outside. We have 1/3. Take the integral, ln of u. So ln of 3x plus 2 plus c. So the main reason these are so easy is because you just kind of know what your u is going to be. But they're designed to be it. They're designed to have the du on top. It gets harder when you don't know exactly what you have to do. Like this one. Doesn't this one look harder? Because, so you might start right away in saying that like u equals x squared plus 1, and so that du is 2x. But we have an x squared on the top. That's kind of the main difficulty here. So what are we going to do? I mean, to me, what's shouting out to me is that we've got to split this up. We've got to split this up into 3 separate integrals. Because the middle one we can do by substitution, and the other ones we're gonna have to think about some different stuff to do. So we have that. We have the integral of x over x squared plus 1. And we have the integral of 1 over x squared plus 1. Okay. Well, so bit by bit, the last one is actually the one that jumps out to me. And you just have to know the integral of 1 over x squared plus 1 is the inverse tangent of x. Right? So that kind of shows me that we're definitely going to have some problems here because the answer is definitely still going to be in it. Now, the middle integral, didn't we literally do that exact problem already? We did that right here. Oh, and look, we didn't actually totally get to the answer. But we've basically done it already, right? It was 1/2. I mean, this was the answer, just with x instead of u. So it's 1/2 the ln of x squared plus 1. Yeah. We're not going to redo that if we've already done it. So let's cut it from here and paste it down here. We've already done that one. Now the first one, that's going to take some more thinking, at least for me. Because if we made x squared plus 1 the u, then we'd still get the du with the x squared. Which ain't the end of the world. But you wonder if there's some other options. And I think the option that I want to try for, at least first off, is I know a lot of times when I've done these integrals of the day, is if I do the division, it ends up being easier if I do the long division. I'm trying to remember which one goes on the outside and which one goes on the inside. So this is going to go on the inside, and this is going to go on the outside. Is this going to be any use at all? It's going to get the remainder. Oh, I can just do that on my own, though. Here's how you get the remainder from this. So you rewrite. So notice how we got the last two integrals. So we did u substitution, and we did inverse trig. And now on the first one, I'm going to do a little tricky trick where I go like that. So, of course, it's the same because the ones cancel out. But what that allows us to do is that in an interesting way. All right, maybe we need to go back to the drawing board with this right from the beginning. Oh my gosh, we definitely do. But let's finish it out. Because look at what we end up with here. We end up with the integral of 1. We can split this up minus the integral of 1 over x squared plus 1. And this is minus the inverse tangent of x. So even though it does end up with that, they end up canceling out. And this is just x. So these cancel out. All we end up with is x plus 1/2 ln of x squared plus 1. Yeah, that's because what we should have done from the very beginning is rethought about this as x squared plus 1 plus x over x squared plus 1. And then straight from there, hearted it like this. Because that right away allows you to rewrite this as 1 plus x over x squared plus 1. And then we got that integral above, and the integral of 1 is simply x. That's the way to do it. And that's why integrals are so fun. There's so many different ways to do them. And as long as you're doing things right, things will cancel out, and you'll end up with the same thing everybody else has. All right, so what about this one? So my first instinct is to make u just x plus 1. But you see, that's a problem. Well, it's not necessarily a problem. That's an idea. Maybe that is what we're going to have to do here. Because another idea is, like, if I multiplied this out and made the entire bottom u, so this would be x squared plus 2x plus 1. So if u is x squared plus 2x plus 1, then du was 2x plus 2. That would be nice, but it's kind of hard to just add and subtract it too. I mean, we could try to do just what we did before. Let's try that. And then I have another idea afterwards. So if I do that, if I do the plus 2, I'm definitely going to have to do a minus 2. But I can separate that out now. So I have the integral of this minus the integral of this. I still have to heart it, of course. That's legit. That's super legit. So what do I have then? This is the integral of, because this is the dx. So you see we have our entire du right here. So there's a dx on the outside. So this is 1 over u du. This one, we actually have to do a different u. So I'll use v. I'll say that v, because here we are going to do v is x plus 1. And then dv is just dx. Because then we're going to have 2 over v squared. Or even better, say v to the negative 2. Because then we're just going to use power rule on that part. Yeah, we're just going to use power rule on that part. So what do we end up with? The ln of u, which is x squared plus 2x plus 1, minus power rule here. So 2v to the negative 1, but then divide by the negative, so then add. So that ends up being the ln of x squared plus 2x plus 1 plus 2 over v over x plus 1. That's pretty interesting. We could even go further or just write it differently because this is x plus 1 squared from the beginning, right? So we could pull this 2 out to the front and say that this is 2 times the ln of x plus 1 plus 2 over x plus 1. Can't really combine that any nice way, but that would be the answer. Doing it that way. Yo, what's up, FTE fans? Okay. What's up? What else? So I wanted to do this a different way. So that was super cool, adding 2 and subtracting 2. That's a super cool way to do it. The way that I probably would have done it is I would have said the same thing to start off. Or would I have? No, I wouldn't have. Yes. What would I have done? I would not have done the same thing to start off. What I would have done is right from the top, right from the get-go, say that u is equal to x plus 1. So that du is simply dx. So that gives us the integral of over u squared. But then what about the top? Because we don't have the x in the du still. So it's like we still have that x there. So what we do from there is we use this equation here where we solve for u and we solve for x. So we know that u is x minus 1, or x is u minus 1. And then we put that here. Still have the 2. So I'll go 2u minus 2 du. So see how we just straight up replace the x. We just solve for x and wrote x in terms of u. That's super legit. You can definitely do that. And so from now, we kind of end up with the same scenario as before. Well, now we could do u substitution again if we want, sort of. But I'm not even going to... I wouldn't do substitution here. I would separate this up. So we have the integral of 2u over u squared minus the integral of 2 over u squared. And that pretty much just leaves us doing the same thing we did last time, because these u's cancel. So we have 2 times the ln of u. And then here we've got to use power rule. So this is 2 times u to the negative 2. So we'll move the power to the front. No, we'll increase the power by 1 and divide by the new power. So like before, that's going to turn to plus 2 over u, because it'll be u to the negative 1. And then this time, remember what our u is. It was x plus 1. And so that's how we end up with 2 times the ln of x plus 1 plus 2 over x plus 1. Which is the same thing we got last time, right? Yeah, absolutely. And we didn't even have to like simplify at the end. We went directly to 2 times the ln of x plus 1. That's what I would do. All right, how many more we got? 3, 4. Wow, we got a bit more. This is a long section. All right, so what's next? We got to solve this differential equation, dy over dx. That just means integrate both sides, right? Just a little weird that it's 1 over. Well, let's think. So, actually, that's not weird at all, is it? So we're gonna do. Well, first off, we're gonna solve a differential equation. We gotta get the dx over here. So we're gonna go dy is 1 over x ln x dx. So now we can integrate both sides, and just get a y on this side, and then all of that. So what do you make the u here? So it's a little weird. I think we're going to end up with quite a strange answer. But notice how when we make u the ln of x, so then the du is 1 over x dx, we have that right here already. So all that we're left with is the 1 over ln of x, which is u. So we literally just have 1 over u du here. So then when we do that integral, it's just the ln of u. But then what is u? U is ln of x. So it's the ln of x. Which is a little weird. I don't think there's any good way to simplify that. Let's look at Desmos. If you're thinking I wrote a dn, it's probably actually a du. Yeah, I wrote du equals dx. You gotta listen to what I say with my handwriting too sometimes. I need to be better with the neatness though. I don't know why I ignore the grid. It's like it's not the right size. Maybe I need to resize it. What were we even trying? We weren't trying to do a definite integral. That was the problem. So how do you do that then? You go from 0 to x if you just want it to graph of 1 over... Just have to use a different variable. Go j ln of j. I could have just typed it in. I was already in the keyboard. And then dj. dj. And then that'll graph it. So is that the same as the graph of the ln of x? No. It's not. That's definitely right. I mean, plus c, but that's just going to move it up and down. Is it just because I'm missing absolute value things? That almost makes it worse. Okay, yeah. Oh, well, then it's just a plus c thing, so it's actually like it should be minus 2. Okay. I mean, we're definitely right on that. I know what I'm doing. I mean, that's definitely right. Yeah, that's what you're thinking of if you think of dn. I'm using du here. Alright, let's go on to the next one. So this is like a derivation. Like, what is the integral of tangent? It's actually kind of useful to memorize that. But if you don't know it, we can find it pretty neatly, pretty easily. So what do? We got to rewrite it. So this is definitely not clear. That's why it's nice to actually memorize this, because it's not super straightforward, not super clear what you would do. But what you want to do is you want to rewrite tangent as sine over cosine. Sine of x over cosine of x. dx. Just because, look at what you can do then. And this is why computers can't really do integrals. They just do it like brute force ways. But humans, we can do so much better because we can look ahead and we can say that we just noticed when we make u cosine of x, then du is negative sine of x, which is what we have on top. All we're missing is the negative. So we'll add 1 on the inside and the outside to cancel each other out. And then we just have 1 over u du with the negative on the outside. So negative ln. Ln of what? Ln of u, which is cosine. Plus c, cosine of x. And then, like, that's pretty clear. When you go to check yourself, like I'd always recommend, and you take the derivative, you would get 1 over cosine, or negative 1 over cosine, and then chain rule, multiply by the derivative of cosine. So multiply by negative sine. which will leave you with the negatives canceling out, sine over cosine, tangent. Beautiful. So that is really nice to remember. What is the integral of tangent? It is negative ln of cosine. Technically, absolute value of cosine. All right. Now this one. Secant, again, one that I think is nice to just kind of memorize. Because I'm having trouble thinking of what I would do here. I mean, what is secant? Secant is 1 over cosine, that's for sure. But that's not super helpful. If we took the integral, if we took the derivative of secant, it would be secant tangent. But I don't think there's any good ideas to be had there. We could do some multiplying by stuff, but not by secant of x, just by numbers, really. I mean, we could do it if we kept it all on the inside, though, right? I'm just having a hard time seeing how that would end up being useful. This is a thinker. What are we thinking? What are we thinking? I'm going to pause the recording, actually, because I've got to think about this a little bit. Whoa, there's no pause recording button? Something weird is going on with my OBS. There's no pause recording button. Well, I guess I'm not going to pause the recording. All right, how do you take the integral of this? 1 over cosine of x. Or secant. If it was secant squared, that'd be something. I can't turn it into secant squared, can I? Y'all got any tips for me in the chat? What would I take the derivative of and get secant? I mean, what if it was secant over tan? I'm just going to... Well, secant over tan, no. Then I got to use the quotient rule and stuff. And then there's like really crazy stuff that's going to end up happening. How would I take the integral of 1 over cosine? Or just the integral of secant? I can't really square both sides. That's not really a thing. If I said u was cosine of x, then du would be... If I said that u... Or what if I just said that u was secant x, and then du is secant x tan x dx? But yeah, that's just absolutely nowhere to be found. You can't just make that up somewhere. And it's the same problem with cosine. It's just a little simpler because if I did this and then I made u cosine, then just like before, we'd have negative sine. But there's no negative sine anywhere. Let me try to substitute 1 for another term. Well, the integral of 1 is just 0. So I don't think that's going to be useful. Maybe just what's the derivative of the ln of secant? Wait, what? That's tangent, isn't it? What did we just say? We just said the derivative of the ln of cosine was tangent. But here, what's the derivative of the ln of secant? Oh, well, secant and cosine go together. That's why. Yeah. The ln of secant is also tangent. Right? Because you'd go 1 over secant and then multiply by the derivative of secant, which is secant tangent. So it cancels out and just gets tangent. And the reason that makes sense still with this is because if you have a negative outside the log, you could rewrite this as the ln of cosine to the negative 1 over cosine, which is the ln of secant. So that's cool. But that's not helpful at all for us here. But how would you, what do you mean substitute 1 for another term? If you don't mean use substitution. I'm sure I've done this before. I mean, what if I did... It is a fact that... this is kind of weird with the square roots and stuff, but we know that, what is it? 1 plus... Secant squared is 1 plus tangent squared. So this is the square root of 1 plus tangent squared. But then still, if I did like u equals 1 plus tangent squared, I'm going to have 2 times tangent times secant squared as my u, and that's nowhere to be found. So that's no good. I'm just like taking shots in the dark now. As if I get it, maybe I could like reverse engineer it. So the ln of 1 over tan is 1 over tan times secant squared. So that's nothing. Well, I mean, that's something. What's secant squared over tan? Because if I remember the diagram, secant over tangent, cosecant is equal to secant over tangent. So this is equal to secant times cosecant. Oh, that's like what we had before. Oh, yeah, we already did that. That was an answer we got before. This is tough. Do we really have to go look in the internet for it? That's okay. That's what Google is for anyway. We just gotta make sure we understand their answer. Let's ask the all-knowing, actually. Because they'll give us some steps. Oh, I'm not logged in. This should be long, or it should be quick. Boom, 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 boom. Oh my gosh, come on, come on. How do you integrate secants? To integrate secant, you can use the substitution method or integration by parts. Oh, I didn't even think about integration by parts. I haven't learned integration by parts, though. So we're going to definitely be trying to do... Oh, wow, we did that. Wait, what? That's not true. Start with the integral of secant of x. Use the identity secant squared minus 1 equals tangent squared of x to rewrite the integral. Is that? What? That's not the same thing. Simplify that to be secant squared minus the integral of dx plus c. You haven't taken the integral yet. Why are you plus c'ing? Is that the correct answer? Tangent of x minus x plus c? So the derivative of tangent of x is secant squared. No, that's secant squared minus 1. That's not equal to secant. What the heck are you doing? And you get a different answer down here? What the heck are you doing? Oh, ChatGPT. No. There we go. Here we go. What? Is that what the textbook says? I've been avoiding opening the textbook because I'm worried it's going to crash my iPad because it so often does. Maybe if I let it rest for a second before I have it move, it'll help. Okay, so I gotta come down here. Oh, they did want us to do long division there. We just did it a smarter way. So we did that. They got, yeah, the same answer that we did. We did that. That is how they do that. Man, you got to be really thinking out of the box to think about that. I am not embarrassed that I didn't think about multiplying by secant plus tan over secant plus tan. Holy moly. Holy moly. That's not even going to erase everything. That was awful. So, but let's, with that tip, hopefully we'll be able to figure out what to do from there. I didn't remember that being so ridiculous. So we're going to be multiplying. We're finding the integral of secant of x times secant x tan x plus tan x over secant x plus tan x. Now let's try to figure out why we're trying to do that. Because we're going to go that u is secant x plus tan x, which means that du is secant x tan x plus secant squared of x, which, golly gee, when we distribute that in there, that's precisely what we have on top, isn't it? That's precisely what we have on top. So that tells us what we have here. This is dx, is this entire circled thing here is our du. So all we have is 1 over u du, like the rest of them. We just had to be super smart about what we multiply by. And that's crazy. I wouldn't expect anybody to be able to come up with that on their own. But that's kind of one of those things that happens in math. We don't have to have everybody come up with it on our own. And we don't have to do that from scratch every single time. Now that we have done it once, we can just remember that the integral of secant of x is the ln of secant of x plus tangent of x. And let's just confirm that for ourselves. So if we take the derivative, and a lot of times once you get experience with this, taking the derivative to check your answer feels silly because it literally is just the opposite of what you had before, of what you did before. So now if we multiply by secant of x plus tangent of x, the derivative of secant is secant tangent. The derivative of tangent is secant squared. So now we can see that if we factored out a secant squared, or a secant, we would have the secant of x times tan x plus secant x, and all of that divided by secant x plus tan x. So that would cancel, and we would just end up with secant of x. That's pretty wild. I'm not going to lie. That's pretty wild. But I'm glad that we got to see that. Ha, you didn't get to see it because I didn't change my iPad back. But it is pretty clear after that. We get our u equals secant plus tan. Our du is secant tan plus secant squared. Just take the derivative of both of those. And that makes for a very clean substitution, very clean integral. And you just put it back. And this is everything I commentated through when we were doing that. Yeah, ChatGPT is definitely not reliable for math. But Bing's is better. That's unfortunate. I mean, they're just probably using the advanced version, right? Like the version you pay for. Okay. So now let's do this one. The integral from 0 to pi over 4 of the square root of 1 plus tangent squared. Oof. Well, 1 plus tangent squared, I mean, that really does ring a bell, but not... Oh, yeah, 1 plus tangent squared. That's secant squared. Or is it cosecant squared? So, I don't know how much I've talked about my diagram. I've drawn it, I think this is the third time today, or at least the starts of it. Oh my gosh. I've been drawing it wrong, though. Tangent goes over here. Cotangent goes over here. And this is cosecant, and this is secant. Oh my gosh. That's not correct, is it? I don't know what I'm trying to do. That's not how it works. Tangent is over here and cotangent is over here. Because tangent equals sine over cosine. And cotan equals cosine over sine. Yeah, this is right. So I know that 1 plus tangent squared plus 1 is equal to secant squared. So isn't just this the integral from 0 to pi over 4 of secant squared of secant? Because it's equal to secant squared, but then you take the square root of it. So we're doing the same integral that we did up here, just from pi over 4 to 0. That's weird. So we're going to do the ln of secant x plus tan x. Just from these numbers. That's super obnoxious, honestly. What's the secant of pi over 4? Root 2 over 2, so 2 over root 2. So ln of 2 over root 2 plus the tangent of pi over 4 is 1, so plus 1. And then minus the ln of the secant of 0, 1 over the cosine of 0. 1 over the cosine of 0, that's undefined. That's undefined. What's the tangent of 0? Wait, 1 over the cosine of 0 is not undefined. Cosine of 0 is 1. You bot. Cosine of 0 is 1, so it's 1 over 1. So it's 1. Plus the tangent of 0, which is 0. 1 plus 0. So minus the ln of 1, which is 0. It's kind of what I expected. So the answer should be the ln of 2 plus root 2 over 2. If you combine the fractions, if you then rationalize, which probably would be better, you would end up with the ln, should definitely be better. So it'd be the ln of 2 root 2 plus 2 over 2, which is then the ln of root 2 plus 1. Wow. I'm pretty unconfident about that answer. Let's Desmos it and make sure. But it makes sense. It's weird because it's the exact problem we did before. If it wasn't like that, I would be more confident. I don't know why that makes me less confident, because it's definitely true. It's definitely the same as the problem we had before. So the square root of 1 plus tangent of x, pop squared right there, dx is that, and is that the same as the ln of root 2 plus 1? It indeed is, yeah. It is kind of fun to me that like the answers will get so complicated in these sections. And that's why like a decimal answer is like such dirt for this. Like who even cares? You want the exact answer. ln of the square root of 2 plus 1. All right. Well, this is kind of an interesting idea. What's the average value of tangent of x? So I think we've talked about average value already. So that means we need to find the area under the curve of tangent of x on that interval, and then divide by the entire length of the interval, which in this case is pi over 4. So that's exactly what we're doing. And we've already found the integral of tangent x, right? That was why I said we memorized it. Now we don't have to do it again. We know that the integral of tangent of x is ln of cosine of x. Negative ln of cosine of x. We can confirm real quick, just do it in our heads. 1 over cosine times negative sine. The negatives cancel, so it would be sine over cosine. It would be tangent. Yeah, that's correct. And we want that from pi over 4 to 0. So we go negative ln of cosine of pi over 4, root 2 over 2, minus the negative, so then plus ln of cosine of 0, so the ln of 1, so like most of these, just 0. So the answer is negative ln root 2 over 2. I'm going to make that a little better in interesting ways. And again, logarithms are fun like that. So I'm going to go, well, what do I really want to do? I want to unrationalize it. Yeah, no, this is beautiful. I want to unrationalize it. So that's when, to me, I write this as root 2 times root 2, so I can cancel these root 2's, because then I have the negative ln of 1 over root 2, but with this negative, you can bring that to the exponent, and so when you raise a fraction to a negative exponent, it flips it. So it's going to be the ln of root 2. Or maybe we would want to say 1/2 the ln of 2 if we bring that square root out there. And that's just a way nicer answer than it was before. But we're not done, right? Because we never divided by pi over 4. We've got to do this divided by pi over 4, which, multiplying by the reciprocal, multiply by 4 over pi. These 2's are canceling now. So now we end up with 2 ln of 2 over pi. Or personally, I would prefer to say the ln of 4 by making that the exponent over pi. So the average value is the ln of 4 over pi for tangent. That like tells you so little, doesn't it? That's so hard to estimate. But let's plug in and see how well Desmos agrees with us. So we're looking at from 0 to pi over 4 for the function tangent of x dx. And then after they do all that, we want to be dividing by pi over 4. And that's the answer. Is that the ln of 4 divided by pi? I have no idea. The ln of 4 divided by pi. Sure as heck is. That was a fun section. I didn't think anything in that was that bad. Besides this, but like knowing to multiply by secant plus tan over secant plus tan, that's not really a strategy that you know. I mean, a strategy that you know is like sometimes manipulating stuff. Like up here we did the plus 2 minus 2. You should be able to see that, I think. Or up here where we split this up in an intelligent way rather than having to do the long division. I think you should see that. You got your x squared plus 1 here. So that is the beauty of multiplying by integrals. I mean, it is kind of cool that the only way to do that integral was integration by parts, which we haven't learned yet and won't learn if you're in AB, or multiply by secant x plus tangent x over secant x plus tangent x. So hopefully I'll remember that next time when I'm trying to show somebody how to integrate secant. But other than that, I won't need to know it because this did ring a bell when I saw it. That the integral of secant is the ln of secant x plus tangent x. And it's the reason it's kind of easier to remember is because the derivative of secant is secant times tangent. So here it's just secant plus tangent inside of an ln, of course. But yeah, that was some good practice. So we did logarithms with derivatives. We did logarithms with integrals. But actually, that's not even true, is it? We just did ln. We didn't even do the basic logarithm yet. So I imagine we'll do that next. But next time, we're starting inverse functions.